Good day. I am Ron Michael L. Nene, and today I'm going to discuss my project. This is a type of field effect transistor called the two-stage common source amplifier. Common source amplifier stages are the equivalent of the BJT or bipolar junction transistor common emitter configuration. They have a moderately low output impedance and somewhat less output current capability than a common drain configuration. They have some voltage gain and current gain, which makes the configuration the most versatile FET amplifier configuration. One of the main disadvantages of using the FET or the field effect transistor is that they needed to be negatively biased. If this bias failed, for any reasons, the gate source voltage may rise and become positive, causing an increase in drain current resulting in failure of the drain voltage. Also, the high channel resistance coupled with the high quiescent ready steady-state drain current makes this device run hot, so additionally heat sink is required. The circuit comprises of uh, four or five, apparently five capacitors, six resistors, and two voltage sources, with the ground in the VCC and another ground here in the main circuit. Also, it has two transistors that has two N3819 transistor for the both transistors. To start things off, we are going to do transient analysis. And for transient analysis, you have to type this command. The command will be run transient is the command for this first command. To run 0, 3 and 0. And we will place it here, up here. Then after that, we, in this project, are going to find the bandwidth, the amplifier factor, and the power. For that, we have to find the amplifier factor first. With that, we are going to type these commands, which is not mess to run VIP in. This command is for measuring the peak-to-peak input voltage of the circuit. Next is we will measure the output voltage peak-to-peak, VOPP. Then we will find for the AV, which is the amplifier factor. Yes. Then that is complete. We will place it here. After that, we will run the simulation and add plot plane, and we will find the trace V in V out. And this is the waveform for the transient analysis. Here it is. Then to find some other parameters, we will have to type an additional commands. With that, We will start off with this measure to run I in PP, I in PP, PP, I C1. This is for um, the input peak-to-peak current of the circuit. And to add with that, that is not finished. Oh, sorry. I have to add something else. The output of the current peak-to-peak mesh run I out PP, ID J1 and including the AI that mesh run AI around I out. This is the average current for the circuit. I out PP I out PP slash I PP. And that mesh AP param. This is the average power for the circuit. AV AI. And then here. After that, we will add some additional commands again. We need to find T1 and T2 and the frequency. To do that, we will type these commands. Run T1. Find time when V is equal to 2.5 M. To 2.5 M. The same goes with the strand 2 pair, but there is an additional command. Mesh strand T2 find time when V in is equals to 2.5 M. 2.5 M cross. This is where it goes different. And then next is for the frequency in that mesh FIN param 1 param 1 over T2 minus T1, T2 minus T1. And then there will be an additional commands again for the output that mesh to run T10. To run T10, find time that means run T10, find time when V out say was 250 M. That mesh run, this is for the second one, T20, find time when V out is also equal to 50 M, but there will be cross equals to 3. And then next is for the frequency out. That mesh f out param 1 slash T20 minus T10. So T20 minus T10. And then that will be the end for the output. And last but not the least, with that we can figure out the power. Since the formula of the power is voltage times current, this will be the command for finding the power for the circuit. Mesh power out. Why power out? Because power out is the output power for the circuit, and the output is the one being produced by the circuit. Output power out. I out, I out, PP. Mesh power out, param VOPP times IOPP. And with that, we are done with the transient analysis. After that, we will run the commands. After running, right-click view, then go to the spice error log. And with that, oh, the power out failed. We have to try again. The power out. So for the power out, this will be the command that will be inputted. And to see the power out or the power for the circuit, we will run and then view and spice error log. And with that, here we will see the power. This is the power for the circuit. Yes, that's the power. And it is 1.02 M. 1.02 M. If I am not mistaken. Sorry for the mistake. The power output, where did that go? Here, spice error log. The power output, if converted from decimal, is 102.32, 31 I mean, 102.31 U, which is micro. And for that, we are done finding the power and the amplifier factor. Next is the, what do you call this? AC analysis. For the AC analysis, we have to type a command. And that command will be that AC deck 10G. Then this goes here for the next part of the project. Now, to find the bandwidth of the circuit, we need to find the max dB. The max dB can be found by running the simulation using the AC analysis. By running, there will be multiple analysis, but since we are in the AC analysis part, we'll go with this one. And then, to find the max dB, we will trace the V out. The V out will result like this, and then if you click this will be the magnitude. The magnitude here is negative 5.43626 decibels. This is the maximum dB here. And then, to proceed with the project, we will have to type the command for we to prove that the mentioned max dB and in the circuit is correct. To prove that it is correct, we will have to type this command, mesh AC max dB, max mag V out, max mag V out. I forgot the parentheses. Then after that measure AC max dB max mag V out. There you go. We will put it here and then run the simulation again for the AC analysis. I mean, view then error log. Since we are in the AC analysis, the AVA, IAP, these things that was measured and failed is not being read because it is from the transient analysis and we are in the AC analysis. With that, the max dB is negative 5.4325, it is in the you call this the waveform. If we see the waveform again here, and then we click this, that is the exact value. And if we go to the spice error log, we can see here that the max dB is negative 5.54. There's a slight difference, but they're almost the same. And then, before we finally find the bandwidth, we should find for its components. It is comprised of the high frequency and the low frequency. With that, to find the missing components, we have to type these commands. And that commands are .measure ACFH, find frequency when V out. Is equals to 0.373971. You might be thinking, where did these values come from? After finishing the commands, I will explain it. ACFL for the lowest frequency. Find frequency when V out. Is equals to 0.373971373971. Cross. Then we are going to put it here. For the values, the 0.373971, it is derived from the maximum dB, because the maximum dB will be converted to voltage gain or voltage ratio loss, because it is needed to find the bandwidth and to convert it might as well convert it. It is really needed. And with that, if you convert either it is gain in decibel or loss in decibel, but in our situation, since we have negative value, it is loss in decibel. Then the voltage ratio loss as a result will be 0.373971. By the way, when you are going to get the voltage ratio loss, you should minus or subtract 3 from the loss in decibel because it is in the manual. I have read the manual and it is in that I saw that this should be subtracted to 3, -3. I mean. And with that, we can finally found the FH and FL. Oh, I'm sorry. FL. For the FL, where did it go wrong though? Define frequency. So for the lowest frequency, if we will run the commands that was typed in there, spice error lag, this will be the FL. This will be the highest frequency, which is 28.369 decibels and 137 or 100, yeah, 137. And this will be 28, yeah, 28. And with that, we are done with finding the highest frequency and the lowest frequency. Together, we can solve for the last missing, which is the bandwidth. To get the bandwidth, I will type this certain command. This is optional because there are a lot of commands and I am comfortable with this, so I will go with this one. This is more comfortable for me. Measure bandwidth from FH to FL because in this command, in the equation of bandwidth, FH and FL is needed to find the bandwidth of the circuit. And with that, we will run again the program and then view spice error lag. And with that, this is the bandwidth, which is 6.59 megahertz. And that's quite a lot. And with that, we are finished discussing the project. Thank you and have a good day. God bless.